Hello and welcome back to Earie's 8-Bit Workshop. I'm Earie Salmon and this is part 4 of our Building the TI-99 22 series. At the end of episode 3.5 we were left waiting for a delivery of replacement 74 HCT logic ICs to swap out the suspicious ones with half a TI logo on that turned out to be possibly counterfeit. Well, the new chips have finally arrived. Let's get them swapped in. In this episode, part 4, we'll swap out the counterfeit ICs, build the keyboard and the unicorn board, the modern replacement for the GROM chips, and get everything ready for its first proper power-on test. So, let's start swapping the chips. So here are all the chips that I've taken out of the system, and as I put them out, one thing that I notice, apart from the fact that it has half the TI logo on there, is that they all have ARS. Doesn't matter what the type of chip it is, they're ARS chips. We've swapped out all of the counterfeit chips for 74 HCTs and we're still not getting a picture, so time to do a quick review of the data lines. They start on the CPU, I think it's there is the top one. Okay, 1, 2, 3, I'm actually going downwards, 4, 5, 6, 7, they're all looking good, 8, that looks less good. Do you see how it only comes down halfway? It makes it look like something's actually fighting for the bus. 3, 4, 5, 6, 7, 8. Okay, so the bottom half of the bus is not looking too clever. The bottom half of the bus goes through these two and, sorry, one of those and one of those. It goes through the CPU, it goes through the TMS 9918, and it goes through, I think it's this one here, I need to double check, which is a 74 LS245. From there it actually gets translated into the GROMs and the unicorn board. So let's swap the memory over and see if the problem follows the memory or stays with the slot. Okay, power's off. Okay, and we're in. So let's check the bottom pin there. That one looks okay. Bottom pin there, and that one's not looking okay. So we still have a problem with the lower 8 bits. Now we could swap the CPU. We have got the Pico 9918. But I do still have some 74 HCT245s. I think I might swap this one out first. Oh, and that's much better. You can see how it's going all the way to the bottom now. Okay, let's check it on the CPU. About there. No, next one up. Next one up. There. That's D0, D1, D2, D3, D4, D5, D6, D7, D8, D9, D10, D11, D12, D13, D14, D15, and then nothing. Okay, well, I mean, we now have good data on the data bus. I think probably the next thing to do is move over to the address bus. Most look fine except A1, A2 and A3, which are all flatlined at 0 volts. I've attached the two probes to A1 and A3 so we can troubleshoot pulling some ICs. Reviewing the schematic, we start by pulling the logic chips that touch those lines. Removing A5 showed good transitions on A1 to 3. I've swapped U5 and U8. They're the same chip. Didn't produce any difference in the signals though. Removing A9 also restored the transitions, but with a slightly different pattern. Swapping U9 for an alternative, still no change, so we'll move on. On a hunch, I've disabled all the memory by flicking all 5 channels of the S1 to off. The address lines look alive now, but the system still didn't start. So we turn our attention to the memory ICs. 3 HM62256 SRAMs. Unfortunately, my Retro Chip Tester Pro has let me down here. All 3 failed pre-testing, meaning it doesn't even recognise the IC. So I start working through my stock, testing some CY62256s. Those at least pass pre-test, but fail the functional tests. I've fitted the CY62256s into the TI-99 and it powered onto a white screen. As we don't have the Unicorn board installed yet, this is as far as we would expect to get, but it's proof the system is booting as far as it can. With that done, let's talk about the GROM chips. The original TI-99 4A used GROM ICs, special read-only memory chips that were both on the system board and the plug-in command module cartridges. GROM, short for graphics read-only memory, don't let the name fool you, they weren't just for graphics. Those GROMs could contain program data either standalone or in conjunction with ROMs. which augmented the GROM resident data. The code they ran was written in GPL, the graphics programming language, an interpreted language that, well, helped soak up the system's excessive speed. Only joking. Each GROM chip provided 6 kilobytes of storage. They were accessed through special ports in the CPU memory space. The CPU would write a 16-bit address in 2 steps, first the high byte, then the low byte, to 9800, the GROM address register. After that, the chip's internal counter pointed to that location, and the CPU could read sequential bytes from 9802. Each read auto-incremented the counter. For GROMs that supported data writing, data could be written via 9C02. These quirky designs eliminated the need for external address lines, simplified board design, and, conveniently for TI, made cartridge duplication harder. TI kept GROMs proprietary and never released them to third parties. This limited software availability. Of course, the community eventually reverse engineered and documented them fully, much to TI's annoyance. On the console motherboard, GROMs held TI BASIC and parts of the system firmware. Cartridges used them too, for interpreters or for games. These were custom chips and they're very hard to find today. This is where emulation comes in. In this case, we're using an ESP GROM simulator, the Unicorn board, which is essentially an ESP dev kit fitted with level shifters to convert between 3.3 volts and 5 volts. This daughter board plugs into the TI-9922 and emulates GROMs 0, 1 and 2, including the TI BASIC interpreter. If you've got real TI GROMs, you can plug them straight into the sockets instead, but the Unicorn saves us the hunt. Programming the Unicorn is done with the Arduino IDE. First, install the ESP development board extension. Select the right target board, and then flash the firmware. The default firmware image already includes the proper console GROMs and is designed to work directly with the Unicorn board. We need both the main.cpp file and the grom.h file from the GitHub repo. Dan's preference is to use Visual Code Studio, so his project is laid out using that, but if we copy the files directly from GitHub into the Arduino IDE, it works just fine. Since I also wanted TI Extended Basic, I flashed its companion EEPROM using the TL866 and MiniPro. Extended Basic is unusual. It's partly in EEPROM, partly in GROM, so it requires the correct GROM image on the Unicorn board to work. The Unicorn firmware includes support for this combination, so once the EEPROM is programmed and installed in the system board, Extended Basic works just like the original. With the Unicorn board installed, let's try a test power up. And yes, it's working! Unfortunately, we can't press a key yet as we don't have a keyboard, but the system is alive! Next up, the keyboard. We've got our PCB, our switches, and keyboard stabilizer ready. First, I need to mark off the stabilizer frame and cut it to size. There are a couple of passives to solder on and stabilizing clips. Next, we need to insert all the key switches into the frame. Soldering the switches on is straightforward. Just make sure they're seated evenly before committing to all 50 plus solder joints. The AT-Tiny13's job is to manage the caps lock. Instead of using a hardwired switch, the microcontroller tracks the key press, toggles the line, and drives the LED. Initially I found a bug. The LED strobed instead of toggling. I fixed the code, recompiled it in the Arduino IDE, and generated a new hex file. That hex file was then flashed onto the chip using the TL866 with MiniPro. This way I've avoided wiring up a breadboard and a USB ESP programmer. Just pop the chip into the TL866, flash it and done. The updated firmware is on my GitHub, and I've also sent the fix back to Dan as well. The one logic chip, and finally the AT-Tiny13 microcontroller. Now on to installing the keycaps. Connect the cable, which we will attach to the motherboard, and the keyboard is complete. I've added the alternate function keys to the front of the keycaps using a permanent fine liner and a steady hand, so it looked as close to the original keyboard as I can get. After finishing both the Unicorn and the keyboard builds, don't forget to clean the flux residue off the back of the boards. The usual recommendation is to use IPA, isopropyl alcohol, but I always find that leaves the board sticky. So instead I use a spray-on flux remover. Just spray it on, give it a quick wipe with the lint-free cloth, and the flux is gone. No residue, no stickiness, and the boards look fantastic. Now, if you remember, I was having some strange issues with the NTSC video signal earlier. To solve that, I swapped out the original VDP for a Pico 9918, courtesy of Troy Shrapple. This board is a drop-in replacement for the TMS 9918A and provides a crisp VGA output directly. It's open source, and you can check it out on Troy's GitHub repo. Troy also sells them pre-assembled on his Tindy page. Both links below. I want to give Troy a big thank you. He even express post one of these to me when he heard I was having problems with the NTSC signal. As mentioned in the last episode, since talking to the folks on the Atari Age forum, it turned out that the 10.7 MHz clock crystal was incorrect in the BOM. So now that's been swapped out for the correct value, we also have the option of a composite signal. So there we have it. Our TI-9922 finally boots, displays properly, responds to key input, just working the way it should. Our build here has been allocated serial number 8 of the TI-9922 builds by the guys on Atari Age. Thanks, guys. We replaced the GROMs, the Unicorn board, flashed the extended BASIC, built and programmed the keyboard, fixed a firmware bug, and booted into TI BASIC. The TI-9922 is finally interactive. The updated keyboard firmware is on my GitHub repo, the link below. And thanks again to Troy Shrapple for the Pico 9918 giving us our wonderful VGA display. Thanks again to Jason ACT from Atari Age for the loan of his Pico PEB and his assistance in troubleshooting. Thanks to Ricky Dean for Atari Age for the tips for the mods required to the existing design. And most especially to DHE from Atari Age for the information about the counterfeit logic ICs. In the final episode, we'll be putting everything together, mounting the PSU into a 3D printed box, fitting the system board and keyboard into their case, and doing full final testing. Hopefully we'll also plug in a command module cartridge and write a short basic program, just for fun. If you've been following along, check the description for all the links and the resources mentioned in the video, and if you're enjoying this build, please give the video a thumbs up, like and subscribe to Earie's 8-Bit Workshop, and share it with anyone who loves retro computing. Every sub, every like keeps those projects going. Thank you very much. See you next time. Bye!